Hi, welcome back. In this lecture, I want to talk about a classical bit and introduce the quantum bit or qubits in short. We will see that the quantum bits are nothing else than a generalization of a classical bit. So at the heart of a classical computing and computers and information theory, there is the concept of bit. In the same way, at the heart of a quantum computer and quantum computing, there is a generalization of the concept of a bit that is called quantum bit or a qubit. So let's look at first at the definition of a classical bit. A bit is a unit of information describing a two-dimensional classical system. There are many examples of realization of classical bits. For instance, a bit is electricity traveling through a circuit or not. So if you have a cable, we have a classical state 1, if we can measure electricity going from one part of the cable to the other one. If we don't measure any electricity, then the classical system is in state 0. A bit is a way of denoting true or false, or a bit also can be implemented very easily as a switch that can be turned on or off. An example of such a switch is on these slides. Here we have a switch. If the switch is turned off, this represents our state 0. If the switch is turned on, then we can represent this state using 1. So we can use 1 and 0 implemented with our switch to represent a bit that can be either in state 0 or state 1. For representing a bit and then later on also quantum bit, we use the bracket notation for expressing vectors. We discussed already the bracket notation for vectors. I just want to summarize in these slides now. So we saw that a row vector can be expressed as a bra vector. A bra vector V will be just denoted by this notation here. We can do the same way to represent a column vector. For instance, we have a column vector U. We can use the cat notation. That is the complementary one here. And this is the cat notation. So a U in a cat notation will be just a column vector with all the elements. And then you note here that we have the transpose. So this is actually a column vector. So the major difference from bra and cat is basically one is a row vector and the other one is a column vector. Bras are row vectors and cats are column vectors, and we will use bras and cats for expressing vectors in quantum computing. So if we want to use a bra-cat notation for expressing a bit, a classical bit, we can represent 0, or better, the state cat 0 as a 2 by 1 matrix with a 1 in the 0 row and a 0 in the 1's row. So our state 0 can be represented by this vector with a real number, where we have a 1 that is the coefficient multiplying the state 0, what we called the basic state in the previous lecture. And then we have a 0 that is multiplying the state 1. Obviously here we will have a 1 here because that's what we have. In the same way, we can, if we have a system in the state 1 or cat 1, we can represent this as a vector with a real number with a 0 in the first element of our column, because this is multiplying by the 0 state, and a 1 in the second position of our column vector. So obviously there is a 0, 1 that's multiplied 0 state, and then we have 1 that is multiplied the 1 state. Right. So we recovered the 1 state. So why all this machinery? Well, we want to have all this machinery to express the quantum bit that is a generalization of the bit. So a bit can be either in state 0 or in state 1, which is sufficient for the classical world. However, we saw that the quantum states in the previous lecture can be a blending of different quantum states. Only after the measurement we will have our system in a defined, well-defined state. But before that, we saw that we can have our quantum system in a mixture, what we call the superposition. So as we saw in the previous lecture, in the quantum world, there are situations where we are in one state and in another. That's what we call superposition of state. When we define a quantum bit is the same. So we can have a superposition of the state 0 and the state 1. So in some sense, before actually measurement, the quantum system can be thought as a blending of two states. It can be found in state 0 with a certain probability and in state 1 with a certain probability. So a quantum bit, or a qubit in short, is a unit of information describing a two-dimensional or two-state quantum system. So the quantum system here will give you the major feature of the quantum system is that we introduce this superposition. So we allow, before the measurement, the system to be in a multiple state with different probabilities. So superposition here. So that's the major feature of our quantum bit. So now we can understand why we want to have this bracket notation. So we can represent a qubit as still as a 2 by 1 matrix or column vector with the complex numbers. Instead of having real number like in a bit, so we multiply 1 either by state 0 or 1, we will use two complex number elements, C0 and C1. So now, if you think back about the previous lecture on quantum state, you can understand why we want to have a complex number. Well, we want to have this complex number to express the probability of finding our two-dimensional system either in state 0 or in state 1 after we do the measurement. As we saw in the previous lecture, whenever we have a quantum system, we can use a complex number column vector. And this is typically normalized by we take the norm and then the norm of this vector, and then we take the square. So this number C0 and C1 are actually normalized. This means that are normalized in this way. That means that the C0 square plus C1 square is equal to 1. As we saw in the previous lecture about the quantum state, the module of C0, that is squared, can be interpreted as the probability that after measuring the qubit, we will find our of a system in the state 0. In the same way, C1, the module of C1 square is to be interpreted as the probability that after measuring the qubit, it will be found in state 1. So you can understand that a classical bit is a special type of qubit. Right? So the classical bit is nothing else than a qubit where the elements of our column vector are real value. The qubit is a generalization of this because we are using complex number. So it's much more general because we can use a complex number. So in the classical bit is just a complex number with a real part. So that's why it's a generalization. Qubit is a generalization of a bit. One important thing is that whenever we measure a qubit, so after we do the measurement, we know the superposition tells us something about the probability of finding after the measurement the qubit in a state 1 or 0. Whenever we measure the qubit, then this collapses to a classical bit, to a bit, because either we measure in state 0 or we measure in a state 1. So we saw that this is equivalent to have a 1 for state 0, and this is equivalent to a column vector where we have 0 for state 0 and 1 for the state 1. So whenever we do the measurement, then the position will collapse to a classical bit. So just either state 0 or state 1. So the qubit is nothing else than a superposition of a basic state 0 and 1. The classical bit state 0 and state 1 are nothing else than the basis or basic state of a complex set. Any qubit can be written as a superposition of the state 0, that is this column vector here, and the state 1. So this is also called basic state, or is the basis. And then, as we saw in the previous lecture about the quantum state, we use a C0 and C1 to characterize the probability of measuring our qubit either in state 0 or in state 1. An example of a qubit is the following. So we have this complex valued column vector. So this is our C0, and this is our C1. And then we express this qubit as a superposition of state 0 and state 1. And this number here is related to the probability of finding, after the measurement, our qubit either in state 0 or in state 1. So let's try to generalize the concept of bit and quantum bit to a multi-bit system. So we know that, for instance, the combination of 8 bits is called a byte. And an example of byte might be the following, where we have 0, 1, 1, 1, 0, 1, 1, 1, 0. So using the vector notation the bracket notation we have been using in the last few lectures, we can represent the bits as follow. So the particular state in this case is equal to 1 and 0. Remember that this is for the state 0 and this is for state 1. So we have a 0 defined here, then we have a 1 that is in state 1, then we have a 1 that is in state 1, and then 0 that is in state 0, and so on and so forth. So we can switch from this very complex notation to a column vector notation, where we basically multiply a real number either by the state 0 or state 1. In quantum computing, to combine a quantum system, we use the tensor product of vectors. So we can do these extra steps going from the notation using the combination of different column vectors that tell you if it's state 0 or state 1. And we can do this extra step because in quantum computing, the combination of quantum system is achieved by using the tensor product. And we can express in quantum computing this combination of column vector as a tensorial product of the quantum state. So in this case, we have the state 0, and then we take the tensorial product by state 1. So you see here we can express in this way here. So these are basically two equivalent formulation. The important part is that we use this tensor product to express this. Whenever we combine quantum states in quantum physics, we use the tensor product. So this also arises to yet another equivalent formulation that we will use throughout the course. So we can describe our qubit, our byte, in another way as 2 to the 8 length vector. So this is our vector, and then for each position of this is a number that tell if we are in which state we are. We're going to have 2 to the 8, that is 256 states, and then we put a 1 in the states we are in. So we started from state 0, 1, 1, 1, 0. Right, so we put a 1 here. Obviously, this can be generalized, so we can go from a classical state where we have just one in only in one position of our column vector. We can generalize this to the case of a quantum system where we allow for the system to be in a superposition of a basic state, and the probability of finding the qubit, the quantum byte in a certain state is represented by a complex number. So in quantum world, in order to permit superposition, we need this generalization. Every state of the 8-qubit system can be written as a column vector, where each element is nothing else than a complex number. And then remember that we will need this normalization part, because this number need to represent a probability. So we need to be sure that the norm that is being squared is equal to 1. So this is the last slides, and talk to you soon.